All right, team, let's go. I'm happy to be here. You're happy. We're all happy, right? We're all thrilled to be here. Assignments, thank you very much. So, magic rectangles, right? It's all about the magic rectangles. So, lots of magic rectangles in our lives. There are these things, right? There are the matrices that you're enjoying so much now. There are blackboards. And the best magic rectangle of all is this thing, piece of paper. All right, so today, right, so assignments are in. This is the plan. This is how it works. We're going to hand assignments in on Thursdays in general. Piles are on the sides. I will return them as soon as possible, hopefully next Tuesday, with solutions. And we are 2 weeks away from the first exam. It was a sigh of happiness, right? When you get to really, show your stuff. All right, so yeah, so this is our 4th lecture. We have these 4 more, including this one, and then an exam. All right, good. Okay, so you know where we are, so you know you have to concentrate. So do I. So today we're going to do matrix operations, adding and subtracting. This is some very basic things which sort of skated over to start with. Multiplication, which turns out to be tricky, strange, and weird, right? 3 times 4 is the same as 4 times 3, but not so for matrices in general. And then we'll get onto this business of inverse. So there are lots of different ways to do multiplication as well. So that's the important thing. There are different ways to do this, and some of them are greatly empowering, right? We want to make ourselves more powerful with our magic rectangle manipulation. We'll talk about inverses, which some of you will have seen in other areas. So this is for square matrices only. Let me add that, square matrices only. There are special weird things you can do for rectangular ones, but these are n by n's only. I'll repeat that, square matrices. So magic squares. Square matrices. All right. And then, this is our friend, right? AX equals B. This is the thing we're talking about through the whole course. And taking detours to where some monks died to find equipment that will help us. AX equals B. Well, we can solve it with a to the minus 1, and we'll talk about how that works and how it doesn't work. We'll talk about how to find a to the minus 1, beautifully, row operations. Fantastic. You've got them all. You've got these things in the box already. And then when things go wrong, because things always go wrong. Right? All right. What else do I need to tell you? Oh, yeah, so I guess I don't need to show you this, but in the assignments, I'll try to do this more and more. The tweets are coming thick and fast. Some of you have interacted with Matrixology Vox, and to your benefit, I think, so it's been good. If you look at some of these, there's a print version and now a sort of an online version, which has little video hints built into them. I know, it's crazy. Okay, all right. So there's a PDF with little videos from YouTube built in. All right, so that's going to happen as we go along. All right, all right. I'm going to tell you some things. Okay. So matrix operations. Really very, very nice. What is this? Chemistry. Oh, dear. Okay. Frightening stuff. Okay, so let's see. So matrix operations is a how-to. If you are involved with the book, I should tell you these things as we go along. It's section 2.4. You'll find it in there. Of course, I have my own rendition of all of these things. Okay, so number 1. So this is simple stuff, right? So this is going to be the first ones will be simple. So the first thing is scalar multiplication. Scalar is, well, it's a good word, but it is obfuscatory, as is the word obfuscatory. Scalar, scale. So it's about changing the size of something. It's something you can scale with. 3 times something, a third times something, whatever it is. So this is just a number, a scaling number, right? You've heard this everywhere. Makes it sound good. By the way, numbers num, letters let. It's important. So it's built in, right? It's built into the language. It's very sneaky, the alphabet people. Okay, let's num with some numbers. Right, so 3, this sort of business. I'll just give you some examples. This carries over from things you've learnt in elementary school with sticks and stuff. Right, 3 times 2, 3 times 1, 3 times minus 1, 3 times 3. So if we're multiplying, this is a number multiplying a matrix, this kind of thing. So just a little number. So we just multiply element by element. So it's element, or elephant if you like to say elephant. It's fun to say elephant. Element by element. 3 times 2 is 6. Now this is spectacular. 3 times 1 is 3, so we're warming ourselves up. Like just a few looseners here. 3 minus 1, 9. That's how it works. We do this a lot. We need to do this a lot. Okay. Should I say this? Okay. So I won't confuse it. All right, so that's one thing. So here's an important kind of definition. We're going to say the ijth entry. We're always going to have the same kind of rules as we go through. And I've lost my piece of paper. I was going to have a T-shirt cannon today, but you know the funding is not so good anymore, right? All right, maybe I can return your assignments with T-shirt cannons. Okay, so let's see. So I have to amuse myself, people. Okay, so we've got A. So in general, so this is a notation thing. Very important. So in general, we have some A matrix. This is M by N. It's good to write it underneath it like this. So this means M rows. I know I've said this, but I'm going to say it again. M rows, N columns. And we use this kind. So we capital letter. So this is a capital letter. This is the font that I have chosen, right, with this business here. So we'll say the entry, or the element, in the ith row, jth column, very basic stuff. It's always mn, it's always ij. You have to really concentrate. Sometimes these things will flip around in weird ways, but all right. It will be aij. That's all, lowercase. Well, we'll try to do that as much as we can. So there's aij. And so in general, 1 is less than or equal to I, which is less than or equal to M. And 1 is less than or equal to J, less than or equal to N. Right? So those I goes with M, J goes with N. All right, so we're going to do some abstract things too, where we talk about a matrix A and a matrix B and a matrix C. They could be any size, right? 50 billion by 323. Fine, we'll get results for those things. Sometimes you will see this. So sometimes see this. This is a useful notation. We'll write A is equal to this. It's a bit of a funny notation, but it says take the elements and kind of blow them up into a box, into a matrix. Right. All right, that's exciting. So chair, who needs a chair? All right. Good, good, good. So if you like, this is T times A. The ijth entry of this guy is equal to T times A ij. How's that feel? So this is a matrix. It's an m by n matrix. We're taking the ijth element, and it's equal to just T times the ijth element of A. Seems a little obscure, but basically we're saying second, let's say the second row, first column, this entry, minus 3, is equal to 3 times minus 1. Right. I know. Okay, so addition. So that's scalar multiplication. Fine. Addition. Good basic stuff. So now we can always do this. We can take any matrix, we can multiply by any number. Matrices, remember, can be vectors. Vectors are just very thin matrices. Very thin matrices or very long ones, right? You can have row vectors go this way, column vectors go this way. So we kind of just can't say vector, actually, in matrixology. You have to say row vector or column vector. You have to be a little careful with that. Also exciting. I know. All right, so addition. So A plus B only makes sense, it's only possible or makes sense if dimensions of A and B are the same, right? So this is a simple thing. So we're warming up to multiplication because that's a hard thing. Right, they have to be the same shapes. This plus this is okay. That's okay. This kind of shape plus this thing, not okay. Right, they have to be the same shape because we're going to add entry by entry. It's completely reasonable what we do. No surprising things here. So, example 2, 3, these exciting numbers, 0, minus 1, 1, plus. All right, see if you can do this. This is just a little warm-up thing. Let the blood flow through your heads. Equals the same shape. I want you to write down what the size of this thing is. What are the dimensions? Right? Dimensions means m by n. Just write underneath it. It's very nice to do that. It will matter especially when we do matrix multiplication. We need to really be careful about dimension. So it's very useful to do that. So you should have a 3 by 2. 3 rows, 2 columns. Is also a 3 by 2 over here. So this is okay. This is a good thing to do. Add them together. Not hard. All right, so we get 2 plus 1 is 3. 3 minus 1 is 2. 1 plus 2 is 3. And 0 minus 1, did I get it right? Let me get it wrong for you. That would be great. Minus 1 and 2. How did I do it? Yeah. Well, if I got it wrong here, I got it wrong there too. All right. Okay, so this is not hard. This should be okay. We're good. That's it for adding and obviously, you know, if you're subtracting, fine, it all works the same way. If you have a multiple here and a multiple here, we'll play in, subtract, whatever it is. Fine? Okay, good. Easy peasy. Okay, so things get hairy and crazy banana town. Crazy pants banana town. I need to get my statements right. When we go to multiplication. All sorts of things. Okay. Okay. Multiplication. How are we doing? All right? Yep. Okay, let's do some multiplication because this, you have to consider. This thing's going to explode here. So let's have a definition. Well, let's work up to our definition. So the first rule, the first requirement, these had to be the same shape for addition. It's different. Now we have multiplication. Let's say C equals A times B. Right, so this is multiplication. I'm just going to put them next to each other. I mean, I want to mention the font choice again, by the way. So X and Y, cursive, very nice. We can differentiate between the multiplication sign. It all goes horribly wrong if we have X times. Okay. All right. I'm defending my behavior. All right. Okay. So C equals A times B. This is only possible if this is M times N, and this is N times K. So this is the kind of thing you want to write out over and over again. What are their dimensions? These must match up. We're getting there. I've given you, many of you know how to do these sorts of things, but we're just working our way into it. All right. And the result will always be, so this is just giving you the overall structure. So the M goes to here, and the K will be here. Right, so it's only okay. So this is the first requirement. So A times B, only okay if the inner dimensions match. So what does that mean in terms of the columns or rows of A? Let's write it in. So it's this, two things have to match. The number of rows or the number of columns of A has to match the number of rows or the number of columns of B. Right. So the number of columns of A must match the number of rows of B, which gives rise to all sorts of goodness. Okay, good. And so this is sort of, I'm kind of putting things possibly not in the best order, but let's see. So we've got this notation now. Slippery. Okay. ijth notation like this. So the definition is that the ijth entry of this guy is equal to the sum from k equals 1 to, I guess let me use a different thing. Let me use a different thing. Let me make this, yeah, all right. All right, k, let's make it, no, I can't do that. No, all right. Voices. K equals 1 to n, and this is going to be A, the k entry of this guy, and then a B, and it's the kj entry of this guy. So what is this thing? So this is really the ijth entry of C is the dot, and we'll do examples, and then we'll see how we can generalize this. That element is the dot product. This is a dot product. These guys match here. So it's this is the dot product. This whole thing here is the dot product. Let me try and draw you an abstract picture of this, of the ith row of A with the jth column of B. So let's see if I can sketch this. All right, so this is going to be, all right, I did it. This is MK. This is our C. All right, so it's just an abstract story here. Some dimensions, M and K. So they have to match up with these ones here. So this needs to be dimension M. And then let's say this is N here. And then we would want K this way. I should make a bigger N. I'll make a bigger N. Get you a better picture. Okay. Let's make that N. K. And this is N here. Sorry. K and N. N, N. N and K. Let me get these pictures right. So this is M rows, columns. Am I losing you people? What's going on? Rows. Now it's n columns here, but it's n rows here. These are rows, and these are columns. So this entry, ij, let's call it ij here. This is I. Give you another color. This box in here, this I in here, and j. That single number there is the dot product of this row. Right, this is the ith row and the jth column. Jth, it can be here. Jth column. Jth column or golem. Okay. So there are going to be m times n such dot products. M times k such dot products. I should say that. This is the resultant is an m by k. There are m times k boxes in here, entries in here. Each one is a dot product. Right? So the first 1, 1, that 1, 1 entry is the first row dotted with the first column. This bottom one is the last row dotted with the last column. This is the definition. We're going to do some examples, and so you can feel like you understand this thing. But you've got it there. All right. Let me do some examples. Yeah. Yeah. How do we feel about this? How do I feel about it? Lecture 10, 10, 10, 10, 10. So let's just do an example, and we'll come back and we'll do this in different ways. Sorry. I'll try to do this for you. I failed. I generally fail. That's why I put that little thing down there. Okay. Okay, let's do an example. Try to fill this in. You can come back to this thing and look at it. Try to understand it. Let's do a tiny example. So here's an example. 1, 2, minus 1, 2, 0, minus 1, 3, and 2. So it satisfies what we want. This is and it's nice to write it down. It's a 2 by 2. So we'll have some different dimensions to make it a little more interesting. 2 by 2. So these things match. So this is OK. This is our A. This is our B. And this is the resulting shape here. Right? So C, this is C equals A times B. So C's shape is 2 by 2. And I know they're all 2s, so that doesn't really help, but I'll connect which 2s they are. 2 and this 2. So it's dot products. You just have to remember these crazy things, dot products, right? So you take this row, multiply it by this column in a dot product fashion. So it's 1 times 0 plus 2 times 3. So let's write out the whole thing. So the first entry here is 1 times 0 plus 2 times 3. And then this dot product here. So this is the first row and the first column. This row, so the first row with the second column, so it's 1 times minus 1 plus 2 times 2. I'll show you something weird about this matrix in a second. Minus 1, this dot product, so now we're on the second row here and the first column. That goes here. The second row and the second column here. So minus 1 times 0, and then plus 2 times 3. And then this dot product over here. So you can see this is laborious, which mathematicians seem to like, plus 2 times 2. But we're going to lift our way of doing multiplication up to more and more general ways, or sort of, depending on the problem, we'll be able to do it in better ways. So here are our 4 dot products. The resulting thing, 6, 6, minus 1 plus 4 is 3, 5. All right, so let's try this. This is AB. What's BA? So this is another example, BA. So see if you can do this one. I'm going to rewrite it around this way. It's fine. They're both. It's a 2 by 2 and a 2 by 2. So we can do this. 1, 2, minus 1, 2. So calculate that. All right, we're going to have to work very hard to get into this whole course. It's a lot of work. OK. We're building up our matrix muscles. So you should have this. I'll just do it for you. I mean, I'll just put in the numbers. So it's 0 times 0 plus minus 1 times 1, 1. This dot product here is a 2 minus 2, 0. Did I get that right? No, it's this dot product, so it's 0 minus 2. And then 3, 2, so it's 3 minus 2 is 1. And then 3, 2 here, so we get a 6 plus 4, 10. Did I get it right? Positive 2. Let's crowdsource it, humans. We're going to vote. We'll vote for the correct answer. That's how math is done, by voting. OK, so some science is, which is very strange to me. All right. What do you notice about these two matrices? They are different. They're not the same. They're not the same. So this is a very important observation. Huge observation. That's a technical mathematical term. Observation. AB is very often not the same as BA. Exciting, right? Exciting. OK, so, and if they are, it's kind of special. We jump up and down and we clap and stuff like that, right? So we get excited. If AB equals BA, we're often quite excited. We're excited and happy, and we say, obviously you can edit that, and we say A and B commute. They commute, which it's not what commuting. Everyone hates commuting actually, but this is the best kind of commuting. Quantum mechanics likes this commuting, right? You can, or you may or may not be able to commute operators. It's actually connected, same kind of story. Momentum and spatial position. And what is the other one? Yeah, OK, so they don't commute, so you can't measure them at the same time. That is somehow connected to this. Anyway, all right, but we're just going to do it with matrices, just numbers in boxes, no physics, it's OK. So that's a big deal. So there's a very good reason that this is not true often. Let me say that. These guys, 2 by 2, 2 by 2, we could swap them, right? We could swap them. So let's say this is actually a definition. Let's say we've got A times B. I shouldn't write up here. I can't see it either. Note. If this is AB, and this is, I guess I've done it like this. This is m by n, and this is m by k. Right? These guys match up. That's by definition. Right? So if AB is OK, right? Let's say so. So given is OK, right? That's this bit here. The inner dimensions match. Then what do we need? We need something else if we can even just talk about what BA is. Right? Then BA is only computable, only sensible if what? Did you say, I heard it was m equals k? Yeah? Yeah, good, right. And so, and the way to handle this and make it very clear to yourself is you just write the dimensions under the matrices all the time, a little bookkeeping. So let's put under here n by k and m by n. And we've had this, we've said these have to be inner products. You can't have an inner product between two vectors of different lengths. Everything explodes, the universe is bad. Einstein will come back with his funny hair and say things about God and get upset. Suck it, Einstein. All right, so we have K and M. They have to, so K must have K equals M. Interesting. Good. For it even to be defined. And there's one more thing. So that's just a start. So that means this kind of thing is OK. So we could do this. So if this was B and A, sorry, if this is AB, then this would be OK. Let's say this is, just for numbers' sake, this is a 3 by 10 and a 10 by 3. Then that's OK. It's a weird-looking thing, but B times A will be, we're just going to stick them like this. That's actually fine. This is a 10 by 3, and this is a 3 by 10. So this is we'll get to these. This is a funny looking calculation, right? But it's actually a thin matrix and a wide matrix. But those dot products are fine. Row, dot product with a column. That's totally fine. So what's the overall shape of these? So C has what dimensions in this case? What's the resulting dimensions of this blob? I could put it down here maybe. C is a 3 by 3, right? The outer dimensions, which is in this case rows and columns here. This one, 10 by 10, which seems kind of weird, right? Because now you've got 100 entries in this thing, and you just started with 30 and 30, so there's a bit of an inflation here. And it turns out we'll understand that. We will understand that very deeply, that C actually should have a lot of kind of redundancy in it. You can't grow information. All right, so C is 10 by 10. So that's a terrible attempt to write a 10. OK. So these aren't even the same shape. So we can't have AB equals BA, right, in this case. So we see, for this example, that AB just can't even, without doing any calculations, doesn't matter what the numbers are in the boxes, right, equals BA. Even if they're both well defined, right? Even if both are OK to do. What am I saying? Both are OK. Is that all right if I say OK? Like they're OK. You can make them. You can compute them. They're not. Right. What do we need to even? We are excited about AB equals BA. That's true. So what will we need for AB to equal BA, regardless of the? What shapes do A and B have to be? Right, that's right. But square in general. Yep, square in general. Good. All right. So, if AB equals BA, A and B must both be n by n. So that's just a start. So if someone says, does this, I've given you an A and here's a B, is AB times BA, is A times B the same as B times A? If they haven't handed you two square matrices are the same, they're trying to mess with you. Say on an exam, for example. I don't know why they would do that. But, OK, so that's good. Good. So this is, we're getting into some oddness of multiplication. 3 times 7 is 7 times 3. But now we've got this whole strange zoo of, right, it's really what we have. We have a zoo of objects. We have matrices, any number of columns you want, this way. Any number of rows, any number of columns. And some of them can play with each other, right? So you can only add matrices of the same exact shape together, but when you're multiplying them together, they have to match up only along 2 dimensions, those inner dimensions. Should we move on? Questions? No? We're all right. OK. I know you want to get back to AX equals B. No, I can feel it. So I think this is good. Matrix order matters. So that's a big deal, right? So here's so this is something you write on your fridge or something at home. I don't know. Big deal. Again, another mathematical term. The theorems and big deals. Big deal. Order of matrix multiplication matters. Matters enormously. Sure. So 7 times 3, terrible. 7 times 3 times 4 equals 4 times 3 times 7. Fine. You can do all these things. Blah, 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 blah. Right? But A, B, C, you can't just lazily say, oh, I'd like to put the C first. This is not necessarily. Only in special cases. Special cases where we give them even special. We can't do this. We can't just slide them around. So none of that. Some of you will do it, and I'll have to say, no, don't do that. I've told you now, so please don't do it. So we don't have to have that conversation later on. Okay. You can't do that. All right, so let's go through a few examples and so see, there's this dot product way of doing it, but let's see how it generalizes to more and more useful ways of actually executing these multiplications. All right, I'll take pictures. Good? And then we'll get to this inverse business. Got to get to that. I really don't know what I'm doing with this. All right. All right, fine. Okay, so examples. Let's work with one particular pair of matrices and multiply them together in different ways. Okay. So good. All right, okay, examples. Okay, so there's more than one way. I will say, this whole they're full of these there are sneaky little tricks. We're going to get to some sneaky little tricks. We'll do some maybe today, but we'll start to get these sneaky little small proofs, little proofs. So you have to concentrate. Again, monks. Think of the monks. Okay, so more than one way to perform multiplications. And some are more useful than others. Okay, so let's see. So let's do this one, example 1. I'm going to let you do this. 3, 0, and I believe this is a 2. Yep, 1 minus 2, 2. This is what we're going to play around with this guy. So can this commute? Can we, this is our A, this is our B. Well, let me not ask that question. A good thing, a healthy thing for you to do lots of healthy things. Just to write down here, every time you see these things, just get in the habit of this. It is a 2 by 3. This is a 3 by 2. So you should be able to write down what the shape is of the final thing. Equals. What's the shape of this guy? 2 by 2. It's this. Good. 2 by 2. These things match, so we're good. Okay, AB is good. So that's AB is good here. And this says, this part tells you that C is 2 by 2. So 2 by 2. And again, it's the dot product. 3, 0, 2. Dot product with this guy. Lots of zeros, right? That's good. Minus 3. 3 times minus 1. There's a 0 here and a 0 here. So they blank each other. 3 times 0. 0 times 1, 2 times 2. So that's a 4. Bottom row, first column. That's going to be this entry. 1, minus 1, minus 4, and 0. So minus 5. I'm doing okay? Okay, 1 minus 2, 2. 0, minus, there's a minus 2 here and a plus 4 here. 2. All right, so that's our answer. I'm going to leave that for a second. Okay, all right, no, it's all right. It's all right. It's all right. All right. Okay, so this is just a note that in this case, BA is okay, 2. And it will be what? What shape? 3 by 3. 3 by 3. The whole thing is 3 by 3. Good, that's a side note. Chalk dust. Oh my God. I am very excited about this. All right, let's get through this. And then we'll do some inverses. Yes, so exciting. And then we'll be finished with the course, because once you have the inverse of A, done. Okay. We'll see why that unfortunately is not true. Tragically. Okay. this one. So let's do a, so this is example 2. This is example 1. 1, 2. This is a funny looking one, but we'll get used to it. 0, 1 minus 2. It's not erasing very well, is it? That is to say, I'm not very good at it. Is this okay? Right, so that's the first thing. Is this okay? Yeah, right? So you write down your things. So you write, it's a 1 by 3. This is actually, what I was saying before, this is a row vector. It's how we write it in matrix, in Matrixology. This is a 3 by 1. So yes, good. And the resultant matrix is 1 by 1. So this is actually a dot product. This is how we write, because matrix operation, multiplication is built out of dot products. This is linear algebra's dot product. It's built into it, but this is how we actually also write them. Row vector, column vector. So this is actually 1 times 0, 2 times 2, 1, so there's a plus 2. Right, let me write it down. 1 times 0, plus 2 times 1, minus 2, plus minus 1 times minus 2. Painful, yes. Pain is good. 4. And it's kind of a 1 by 1, right? But we fiddle with this a little bit. Did I get this wrong? We sort of, we just will call this a number. It becomes a scalar. What does it say? This thing? Yeah, that's a very sad little multiplication sign. How's that? 1 times 0. 2 times 1, minus 1 times minus 2. So that's groovy. So what about this one? Here's a weird, so this is also called an inner product. And you'll be able to see the reason for this. It's inner product collapses, right? It collapses things. Example 3, let's do an outer product. These are very important kinds of multiplications. They seem, we're going to reverse it. 0, 1, minus 2, 1, 2, minus 1. Write down the dimensions. Write down the dimensions of the resulting thing. What's the shape of the resultant character here? 3 by 3. Good. Excellent. Matrices. So great. 3 by 1, 1 by 3. The ones, they connect. Awesome. And 3 by 3. That is the size of this thing. So these are weird dot products, right? You're going to take this row, which is just 0, and take that dot product. So 0 times 1, I'll write them out. 0 times 1, and then 0 times 2, and then 0 times minus 1, right? And then 1 times 1, 1 times 2. So we're about to see, oh, so exciting, 1 times minus 1. And then there's a minus 2 times all of these guys. Minus 2 times 1, minus 2 times 2, and then minus 2 times minus 1. They're tiny little dot products, tiny dot products. So another way to think about this, so better to see in 2 different ways, in 2 other ways. Right, so this is powering up your linear algebra. This is taking this multiplication over here, right? We end up with these numbers in these boxes. We could say it's 0 times the first row, 1 times that row, minus 2 times that row. So we can see it like this as well. You just take copies of this row and then multiply them by those numbers, and you'll get the same answer. So let me do it as matrices within matrices, just like Inception, except with the special effects. 1, 2, minus 1, 1, 2, minus 1. Inception fans? No? Okay. All right. You should have in your margin, I'm sure you've scribbled already, but matrices inside matrices. That is totally fine. So this is a kind of a more powerful way to think of it, right? This is laborious, like, one at a time, right? But now you know that all these rows are actually the same. We know that these rows are the same with multiples in front of them. That's going to be hugely important. So observe all rows, by the way we've constructed, are multiples of each other. Of 1, 2, minus 1. Straight away, right? I did say something that was slightly not correct, but it's all right. So what's the other way we could do this thing? We did rows, so we will do columns. So you can think of this column multiplied by this 1, and then multiplied by this 2, and multiplied by this minus 1, and then stacked next to each other. So it equals this as well. 1 times 0, 1, minus 2. So 0, 1, minus 2, 0, 1, minus 2. This is advanced multiplications. Good. And there's a 2 times this guy and a minus 1 times this guy. All right, so if you multiply these numbers together and then put them in, this is a 3 by 3 still. 3 by 3, 3 by 3. But this is a much more powerful way to think about things. And you are psyched. I know you're psyched. You can do all sorts of weird kinds of multiplications, as long as you block things properly. So, so more general block multiplications. Let's go back to our first example. So we've done everything we can really with these two vectors. That's it. This is very nice. I think you should be happy. So let's go back to the first example, which I've got the right thing. Yeah. Back to example 1. So example 4. Back to example 1. So you can divide these things up. So here it is. It's 3, 1, 0, minus 1. I'm just running it out. 2, 2. You can do whatever you want with these things. 1, 0, as long as things balance. Let's see. So 0, 2. I know. Can you read that? I'm having a hard time reading this. So look at this. This is strange. You could say, let's treat this as a blob. And this is a blob. And this is a blob. This is a blob. This is a blob. This is a blob. So this is kind of like, this is a row vector of 2 by 1s. And this is a column vector of 1 by 2s. So you can start to see this is going to work. So we're going to take, it's a big dot product. So it's going to be this guy times this guy, plus this guy times this guy, plus this guy times this guy. There are ways you can do this sort of thing. Let's see if it works. So if we use this division, now it's 3, 1, minus 1, 0. This is just an example. There are all sorts of crazy things. It's that guy dot product, the 0 minus 1 here, 2, 1, plus, I've erased this. It was a 2, 2. Yeah, 2, 2. Gee. 2, 2. And then a 0, 2. Right? This guy is here. This guy is here. This one is here. So are these the right kind of shape? Yeah, right? So all of these are now 2 by 1, 1 by 2. They match. So this is good. And the resultant shape is 2 by 2, right? So these are all what kind of products? Inner products or outer products? These are outer products. So we made this, we did kind of a weird inner product. Now it's outer products. 3 outer products. Crazy behavior. So you can do, if you do these multiplications in the same way that we did it back. It's gone. Okay. You will see that these things add up to give you the same thing. Should we do it? I guess. Yep. Let me remove this little bit here. Some space. Okay, so this one, 3 times minus 1. 3 times minus 1 is minus 3. 3 times 0 is 0. 1 times minus 1 is minus 1. 1 times 0 is 0. Plus 0. So okay, let's think of it in this way that I've told you. Let's do it in 3 different ways. First is just element-wise by element-wise. This one, let's take 0 of 2, 1. Boop, and then minus 1 of 2, 1. So it's minus 2, minus 1. And then let's have 0 copies of this guy, so 0. And then 2 copies of this guy. That was a bit quick, but I thought I was approaching them in these 3 different ways we've just showed. Add them all together. Minus 3 plus 2 plus 0, so that should be minus 1. And then a 5. Let's see if I got all this wrong. That's a 3. What have I done? What's going on? This one? Oh, yeah. I'm trying to do that. Yep. Oh, the senior professors watch you. Okay, so there'll be lashings later on. I kind of enjoy it. Okay, so minus 3, 4. Am I getting this right now? What have I done? This is not right. What's wrong? Oh, that's very bad. This bit? This bit? So cascading disaster. All right, that's good. Look at that. Thank you. Welcome to step in and fix that up before. Yeah. All right. Okay, minus 2. Let's fix that up. So it's minus 2. That is here, right? Yes? So this should be minus 4 and minus 2? Okay. Yeah. 2, and so we've got minus 1, minus 4, yeah, so minus 5 and 2. Okay, as before, amazingly. All right, thank you. All right. Okay, let me just show you 2 more pieces which we'll go over and over again. Right. And then I'm going to start on inverses. Let's start on some inverses. Okay. So a super important way of multiplying matrices together is to do this. So this is going to be a very important thing. So very important multiplication versions. All right, let's call them versions. So one is A times B. All right, so once again, A times B is M times N and N times K, right? That's what the shapes of these guys are. We can write this as A, and I'll use this kind of structure a lot. So this is B1, it's the first column of B. And then the second column of B. I'll write it like this. We've had this before. So this whole thing is an N by K, right? So there are K of these. And there's N this way. N rows, K columns. The K column vectors. We can do this. This is this thing. I'm just saying, okay, it's got these guys. It's A times B1, A times B2. We're going to bring the We can in real detail prove all of these things element-wise, by element-wise. I'm sort of just trying to appeal to a couple of examples as we go along here. This is, what's this blob here? It's m by n, and then an n by 1. So the shape of this is, it's m by 1, right? So this is now, back here we had an m by n. So this is now an m by 1. This whole thing is an m by 1. There are k of them. So again, the whole thing is a m by k. So you can break this guy to, not rows, on the right-hand side, you can break it into columns, and then go and use A on each one separately, like this. That's a very important feature. All right, and let me just tell you the other version. So similarly, I think that's right, AB, you can write like this, is a bunch of, I'll just call them, I'll write a little r there. So it's the row vectors across the top, whatever they are, and then down to A, it's an m by n, right? M. R, we could break that into row vectors, leave our B here, and then we can bring this in. Multiply each row in the same way. So this is A1 row times B. That's a row vector. A2 times B. That's a row vector down to A M R B. Let's get to see these dimensions are right. This is a 1 by n, and B is an n by k. These things match. It's a 1 by k. This whole thing here is a 1 by k row vector. This is a 1 by k. So you've got a stack of these guys, 1 by k. So it's really good to be able to start to think of matrices as a stack of columns or a stack of rows. What do you stack them next to each other? Is that right? Stack works really well this way. OK, good. So this is the whole thing again is an m by k. This will be helpful. And again, you can, and I'll just let you give this as an example. So as an exercise, which I'm sure you'll race home and do, exercise at home is to solve that first example I gave you using this approach. So solve or compute example 1 using these approaches. Right, and we're trying to get this 2 by 2 matrix, which I messed up in my second attempt. So that's an exercise. So leave yourself some space and do this later on. Good thing. All right, that's good. Let me, all right, well, let's do one last thing just to tie up all of these matrix operations. So last piece on matrix ops. Piece on matrix ops. Say you're just told in general. You don't know what the details are. A is a 3 by 5. B is a 5 by 3. And a C is a 5 by 1. So it's really a vector, but I'm just going to write it as a matrix. And D is a 3 by 1. Which ones are OK? So which are OK of these ones? So can you do this? BA, AB, ABD. Can you do these? Orbit desert. DBA. And I'll give you one more. A, B plus C. So the way to do this easily is to take what you've been given and write it underneath everything. So BA, so it's a 5 by 3 and a 3 by 5. and a 5 by 3. So you just write this everywhere, 3 by 5. 5 by 3, 3 by 5. D was a 3 by 1. B plus C, so this is a 5 by 1, and this is a 5 by 3. And A is a 3 by 5. 3 by 5, 5 by 3, and D is a 3 by 1. So then it should be clear, hopefully. You need all those inner things to match. So is this OK? Yes? Yes, right? 5, 3. Yep, good. And now you can do these multiplications in any order you want. You can do BD or AB first. That's fine. No. OK, so this is bad. So this is out. And you can't, the simple problem, you can't add these together. All right, good. Oh, I see. Yeah. Yeah, you can't pad them. You can't pad them. Yeah, that's right. You can't pad them. Yeah, they're different. So these dimensions put them in a kind of a space. They put them in a space. So if you like, you can transform all. So it's 3 by 5, right? So that's 15. So it's actually an object that's living in 15-dimensional space, arranged in a certain way. And so it's different to a 5-dimensional object. Yeah. I mean, yes, you can project down to it, but you can't. Yeah. Good question. Good question. All right. OK. So I think you've got enough there. So let's start a little bit here. We're going to start on inverses, if I can find the right page. OK. It appears to be unlikely. This is page 9, 10. Where's 10? Why would I ask you guys? Oh. OK, so this is just a start on this goodness. What are we, Thursday? OK, good. So here's a start on matrix inverses. And we've been thinking, I know I've given you a lot of square matrices and so on, but we've been thinking in general about rectangles. Now it's absolutely just about square matrices. So this is square matrices only. This is important. As we go through, towards the end of the course, we'll eventually get to the point where we realize that we can turn rectangular matrices into square ones. We do something weird with them, and we can solve all these problems that square matrices are good for. All right. That was sort of a garbled thing I said. But anyway, inside every rectangular matrix is some kind of square matrix friend. OK. OK, good. So this is not true for all, OK? But it's n by n matrices. So we'll drop the, can you read that? That's n by n matrices only. So we write it in this way. So many square, not all, and that's a hugely important thing. Many square matrices have a multiplicative inverse. Multiplicative inverse. Very exciting terms here. Ah, so many syllables. Inverse. And that is this kind of thing. So a to the minus 1, and it works like this. A to the minus 1 times a is equal to a times a to the minus 1 is equal to the identity. This is 1 in n by n. Talked about the identity the other day. 1's along the diagonal. That is our grown-up person's 1. So the inverse can pre-multiply or post-multiply a, and it gives you the identity. You can have very sneaky, weird matrices that only work on one side. That's not right. So must work pre or post multiplying. OK, so let's finish the course. I've been telling you we're very interested in AX equals B. Oh, I'm kidding. It's not true. me take pictures of these silly things that I've written. Okay. How are we doing? We're good? I know this thing I just erased in this business over here, Crazy Town. What we're talking about here, these guys? Yeah, the structure here is these are row vectors with matrices. So inner products and outer products are only for vectors. So, right, so an outer product, let me get it right. Inner product, boom. Outer product, that guy. And they have to be vectors. Yep, good question. Good, good, good. All right. People. Okay. Okay, so one thing is someone hands you an A and they say, is there an inverse? Right? That's a big deal. That turns out to be a big deal. Okay, so this is a big deal. Another big deal. Lots of big deals. Determining if a to the minus 1 exists or not. And computing it. Now, we probably won't have time to do it quite today. We'll see. But the path we take with computing is a row operation path. So you have all the skills. Yes. OK, so our mission, let's remember our mission, which we had on a piece of paper we ate at the start of the, I had to chew it up. Solve AX equals B. Let's pretend right now, let's consider the square matrix version, n by n version. Right, so this is going to be n by n, this is an n by 1, and this is an n by 1. All of those things make sense. N by n, whoop, those guys, okay. That's just where we are now, square matrices. So if we've got an inverse, we're all good. That's great. Right, so if a to the minus 1 exists, and we know what it is, this amazingly turns out to be very difficult, actually, for large matrices. This is a good way to hurt computers. If you're mad at your computer, make it compute large inverses. Inverses of large matrices. Well, let's do it. We've got A, X equals B. This is sitting here, it's true. Let's again, I'm going to put this here. You must always do the same thing. It's equations, right? You've got to do the same thing. You add 3 to one side, you add 3 to the other side. But it's even more tricky with matrices, because you might think, oh, I'm going to put my a to the minus 1 over here. This is bad. Bad. No, right? Pre-multiply both sides. Right? It does not make any sense to post-multiply. People will try to do this. You can't write a to the minus 1 over here because the dimensions don't match up. You've got a vector with a matrix, a square matrix. It explodes. Let me erase some goodies here. Let's look at that and make sure that the dimensions are all good. A to the minus 1, now it's times A times X. Again, we know this, we don't know this. We do know this. We claim we know this. This is an n by n. This is an n by n. This is an n by 1, n by n, n by 1. All good? Yes. Much excitement, right? Boom, these guys are all good. And the result is an n by 1 and an n by 1. So a to the minus 1 times a is the identity matrix. Right, good. Right, this again, it's still an n by n. Have to remember what that thing is. This thing is sitting here, minus 1b. Identity matrix times anything gives you the thing. Right, that's its goodness. let's think about an identity matrix just quickly. So 1, 1, 1, zeros here. It says we kind of have this bigger idea now of multiplication. Let's imagine it's multiplying some matrix C. It says I want the first one of the first row. I want one of the second row. I want one of the third row. I want, right? It just restacks the thing if we think of it in this bigger way. Okay. Didn't happen. Okay, so this is x equals a to the minus 1 b. So we're done. Course is over. Drop the chalk. Okay, not true. Sadly, this is a lie. A to the minus 1 does not always exist, right? And it doesn't exist for fine, quite reasonable systems. Somehow when we talk about, I was talking about lines of best fit to clouds of points, there are problems with those things, for example. Well, all right. Anyway, healthy, good places don't, it's not a bad matrix if it doesn't have an inverse. Let's say that. It's just singular. It's just unusual. Okay, so this is a lie. So let's just add a couple more statements before we wind up, and then the next time we'll figure out how to do this. So here's the problem. So problems, finding, and this is really the big one, a to the minus 1 is computationally very expensive. If we're in a more technical or more sort of numerical class, I know you're doing MATLAB, we can talk about it. We can figure out how this computation scales as we go up through n. Computation is very expensive. So we want to avoid it. Actually, we actively avoid finding a to the minus 1. It's also potentially unstable. Like the computer explodes. It doesn't do a good job. It gives you the wrong numbers because that whole machine epsilon business, which is a scary thing that computers don't know everything, except everything about you. All right, so it takes a lot of time. It can mess up. And of course, this doesn't apply. And it doesn't apply to rectangular systems. So that's going to be a limit. But we're going to get these guys into our heads early on because there's something great about them. M not equal to n. Let me tell you one good thing here. So if a to the minus 1, so more big deals, and we'll finish with a big deal. If a to the minus 1 exists, this is just theory now, really, then we have a unique solution. So we started off with like lines hitting each other means one unique solution. Parallel means there's no solutions. On top of each other means they're infinite. And we started to think about planes. And we started to think about planes in 5 dimensions, and our brains hurt too much. Okay. So the column picture helps. We'll come back to talking about it. If this exists, then we have a unique solution. And if it doesn't exist, then we have 0 or infinitely many. So let's write that down. If not, we have 0 or infinitely many. So this has become a bigger and bigger story as we go on. Infinitely many solutions. Singular, right? Okay, so I'm going to stop there. Assignment 2 will be out today. Come to office hours. Talk to the Twitter thing. And we'll keep going. Good.
Thank you.